Hi everyone, are you able to hear me clearly and see my screen? Great, great. Hi Ali, hi Anup, hi Jamil, hi Jinyang, hi Jitendra, Karthik, Nada, Prashant, Ramana, Sheikh, Stephanie, Tad, and Thomas. Great, great. All right, so everybody is able to hear me clearly. And let me see if I can. All right, let me just see. All right. Okay, so all right, all right. Looks like the sound quality is not good. Let me see if I can check what's happening with is is there a better way? All right, all right. So the sound quality should be okay. All right. So Ali, maybe something wrong on your end. Let me also check my connectivity. So the connectivity, all right, I'm going to switch my network to something else. So please bear with me. All right. So meeting might disconnect. All right. So I have shifted my network and I think there should not be any problem now. Okay. And all right. So let me share the screen again. All right. So, okay. So I hope the network should be good now. And are you able to see my slides in the full screen mode now? Okay, good, good. So today we are going to discuss the big data and Hadoop part. And if you have any questions, please feel free to ask before that. Yes? No questions? Okay. Just give me a second. I'm looking for a remote. All right, I found the remote. Okay, so there are quite a few questions and very interesting questions. I'm hoping that the recording is going on. Yes. Question from Kush is that you mentioned that we will be using Hadoop FS for SDFS access. What's the difference between, okay, all right. All right, let me just check what is the situation. Just a second, just a second. There is something wrong. I got it. All right, all right. So, okay, I hope it's good now. All right. So, Kush, was I able to answer your question related to Quorum General Manager? Till what point were you able to hear? Huh, okay. Okay, all right. So, none of the answers. Wow. Okay, so let me start from the beginning. Extremely sorry for the goof up. Okay. All right, so let's start from the beginning. So first question was, what is the difference between HDFS command and Hadoop FS command? Hadoop FS command is used when you want to do the usual file system things like a user. For example, you want to upload a file, download a file, okay? You want to upload a file, download a file, or you want to change the replication factor. So in those cases, you use Hadoop FS command. Otherwise, you use the otherwise, in case you want to do the administrative work, such as do the file system check, in those cases, you use HDFS command. All right? Did it make sense to you? Question from Manjunath is that they have discontinued Hadoop FS. So basically, they have made a separate command and they're kind of migrating both the things to a single one. That's true, Manjunath. All right. So they are basically kind of deprecating. They're not discontinuing, deprecating it and moving it to separate command. All right. I think they'll be merging both Hadoop FS and HDFS in future. All right. Okay. That was first question. Second was how many containers one node can execute. Second question was how many containers can one node execute. By default, we configure it to 2 or 3 based on how many cores we have on all machines. But we can change the container size, number of containers on one machine. Basically, the other way, the general way of defining containers is number of containers is the total size dedicated to all the containers, that memory. Then that is first size we define in Ambari. And second size is container maximum size. So if you divide the two, you will get the total number of containers. All right. The third question was regarding the quorum general manager. So the quorum general manager is that model whereby the name node and standby or multiple name node keep on getting switched between, keep on getting switched. Okay. This model is called quorum general manager. Okay. This time, was I able to answer your questions? All right. Good questions. So a question from Kush is, Zookeeper is used in order to communicate with name node. If 50% of zookeeper nodes are down, then it will become read-only. So this will not make name node read-only. It is just that switching between name node and standby node will not happen, okay, if the zookeeper is in read-only mode. All right? Did that make sense to all of you? No? Should I repeat? Okay, great. All right. Any other questions at this point? One more question I wanted to discuss was this. Okay, so a question was from the student in the class. The question was that when I'm doing Hadoop fs minus ls slash my directory name and my file name, what is wrong with this? Okay, can somebody suggest what's wrong with this? So this my directory name is a folder in my home directory, and this is the file in my home directory. So do you think this command, let me just, okay, let's say there is a directory called my underscore directory underscore name that contains a file my file underscore name in my home directory in HDFS. Do you think this command is right? Correct. Basically, what you have to do is, in these cases, you don't have to put slash. Slash means root directory. All right? Slash means root directory. All right? If there are confusions regarding this, all right, I'll just, quickly clear it so that I think this is one major confusion point. Okay. So at the top level, there is a directory called, okay, so there is at the top level, you will find slash as the directory. Okay, slash as a directory. This is the top level. And under this, there is, let's say, data. Okay. And under this, there is, let's say, home. Or let's say, I'm just, okay, not home. And let's say there is user. And there is, say, etc. Okay, under user, let's say there is a directory called Sandeep. Okay, and so on. All right. Now let's say this is my current directory. This is my current directory. Okay, and I want to change the directory to, let's say, data. This is my directory where I want to change it to. Or let's say I want to access a file in the data directory from Sandeep. All right, that is the question. Let's say Sandeep is my current directory. I want to see what is there inside data. So you have to tell me which commands are correct. Which commands are correct. Okay, let me decrease the size. Okay, which commands are correct? Number A, okay, Hadoop fs minus ls dot dot slash data, or slash data. That's B. C is, okay. So which of these commands are correct? Or let me just put it a little bit more. Now, A, B, C, and D, out of this, which commands are correct? Our working directory is Sandeep inside user folder. Thomas, our working directory is Sandeep inside user folder. If we have to see what's there inside data folder, which commands are correct? Okay. So dot dot means go up one level. And then again dot dot means go up one more level. And then slash means we go into that folder. So dot dot, dot dot, and slash data. Dot dot, dot dot, slash data. So A is correct. B is also correct. We can also directly refer to slash data. Do I make sense, Kush and Nada? Okay, so you can also try this command, okay, because it's two level up. Okay, so everybody on the same page. So answer is A and B. These are small things, but they generally confuse a newcomer, a person who is new to Unix. What about D? So what does it mean by dot dot? Dot dot means here. So had there been data folder inside user folder, then this command was right. Dot dot means I'm moving from Sandeep, that was my current directory, to up into user, and that's it. Oh, all right, wonderful, wonderful. So I hope everybody is with me on this. Great, great. So feel free to ask a question, because I think even though these things look pretty straightforward, but most of us get confused with this. All right, great, great. Moving ahead. Question from Kush is, in Yarn, the application app master, the role is only to talk to resource manager and manage container. Does it also do some processing? So, okay, a very good question, but the important part is, okay, so, all right, I think a better idea would be to go back to the page where we talk about Yarn. Okay, I think that architecture is important. So question from Kush is, what is the role of app master? So it contains the application specific code. Okay, like for example, the logic how to get the data sorted using many machines is done in application master of MapReduce. Same is the case with Spark. The Spark's core engine actually runs in application master. Okay, so the individual framework's core, it resides individual framework's core resides on application master. Okay, so application master is like your main method of your class, right? Where the whole the main method contains the logic that which piece of code need to be run in which piece of machine, right? When you write a code, there is a main method. In that main method, you decided, okay, we are going to launch two processes, one thread, and so on, so forth, right? In the same way, let's say let's think about MapReduce framework. In MapReduce framework, first data is passed via maps, and then it is aggregated. Now, who does all of this? Like first, let mappers run on every machine and then aggregate it on a single machine, the output of those, and then pass it through after shuffling, pass it through the reducers, right? That logic runs inside application master. So individual containers do their job, but the fiddling between the various kinds of containers is the role of application master. You can always think of it like main method of your class. Main method of your class, if you remember in the coding, main method of the class generally decides. Imagine that you are writing a piece of code where there is a main method and rest of the work is done by functions running either in the processes, separate processes, or separate threads, right? Separate process or threads will be executed on the containers, while main method, which will coordinate will be on the. Okay, so sounds. Thomas, sound is better now. Okay, okay. All right. So Kush, did I make sense to you? All right, wonderful. Okay, so today we are going to talk about the MapReduce framework. All right. So yesterday we talked about this particular aspect. All right. So I want to take you through MapReduce conceptual level first. Last time we did some hands-on whereby we try to do the word count, and we also executed the command using Hadoop streaming. Okay. All right. So, okay, I'm going to take you through a very quick exercise where you all are invited to participate. Okay, so this is the general diagram of MapReduce. Okay, so the entire logic behind MapReduce is to distribute the work on many machines. It's very simple. It's very simple that when you want to get something done using many computers, if you want to get something done, you first need to divide the logic such that the logic executes near the data, right? The first priority is let the logic execute near to the data, right? So, and the second priority is that in the logic, sometimes we might need to bring data together, such as when you group the data, or let's say, imagine there is a huge file which contains billions of lines, and you want to count vowels in that big file. You want to count number of vowels in that big file. So your first strategy would be to break down this big file into small parts, distribute it on many machines, and then on every machine compute the number of characters, and once that is done, number of vowels compute on every machine. Once you have all of that is done, you sum it up, right? You sum it up, and that's what is MapReduce. Okay, so when you have to merge the data, if you need to merge the data, you write the piece of logic in reduce, whereby all the data will be brought to you after grouping. Okay, now on what basis does the grouping happen? Your mapper function would decide. So you write two pieces of logic, one mapper, other reducer. Okay, the mapper piece will have to give out key and value, and reducer piece will have to group the data, will get the data grouped based on key defined by the mapper. It's not necessary that there is a reducer. All right, there could be like there is no reducer, and the data from mappers is directly going into the file system. The example which we took last time, where we doing WC, the mapper were directly saving the data into HDFS. Okay, so this is the general paradigm. Let me also dig a little bit, because this is very important. So this paradigm of distributing your logic, this paradigm of MapReduce, whereby we distribute our logic, is common in case of Spark and Hadoop. Okay, the difference between Hadoop and Spark is in the implementation. Okay, one is in implementation, and there are slightly different syntax. Okay, in one, the process keeps running while the user is interacting. In case of Spark, the process keeps running till the user is interacting, while in case of MapReduce, the process ends as soon as you submit, as soon as job is finished. Okay, now let me ask you a very simple question. All of you, please pay attention. Good that we have all the participants today. So imagine that you have Lord of the Rings textbooks. It's just hardly 50 MB. How would you find the frequencies of the word? Usually, imagine that this is an assignment from your boss in a typical organization, that you are supposed to find the frequency of words, meaning all the words that are existing in these files, how many times each of those words have occurred. All right, just any idea. How would you usually do it? Don't think about distributed computing. If you think about it's good, just think about, just give me an answer, a practical answer on how would you do it. Let's say on Monday morning you go to office, your boss says that, hey, can you just find the frequencies of all the words in this uh, particular folder? What are the things are you going to do? How can you accomplish this quickly? Anybody? Okay, Arslan says if conditional loops. Okay, okay. More details, Arslan. Sapna says find words, maintain the occurrence in an array. Good, good. In an array, or you want to maintain it in a hash table. Kush says normalization, stemming. Okay, that's a little too advanced. Okay. Saptrish says group by each distinct word. Okay. Find words and put in an array, two-dimensional array. Okay, why two-dimensional array? It should be a single-dimensional array. Karthik, I would need more details, please. Nada says using word counters. Okay, okay, that's kind of, you are hinting at hash table. Looping all over the words, create a map, keyword. Perfect. Thank you, Thomas. All right. All right. Use threads and processes multiple files, and okay. Okay, Manjunath says we'll run 3 threads with each thread accessing the file at certain location of the file. Write logic. Okay, that's interesting. That's interesting. and we will come back to this problem. If I don't come back, uh, please make sure that I answer, I address this. Okay. All right. Good. Very great set of answers. All right. Ted says that do okay. Anoop says hash table in the mapper. Good. Hash table in the mapper. All right. Ted says sequential search in the loop and store in the array. All right. So okay. So here we go. Perfect. Perfect. So I think most of you are hinting at this approach, right? There are many approaches. Some of you have actually hinted on next two approaches. I will go through those approaches. Create a frequency table, empty table, of course, in the beginning. A frequency table is like a dictionary. Dictionary contains name and the value, right? Or you can say dictionary contains word and the meaning, right? Usually, and the quality of the dictionary is it's like an array. In an array, you index things by numbers. In dictionary, you index things by names, right? So the quality of a dictionary or hash table is that you can very quickly search for a particular uh, string. Okay, whether it exists or not, you can just quickly search. Hash table is pretty fast. All right. Now question is okay. So that's the usual way of creating hash table. You have a hash table, and uh, it's a data structure provided by the programming language or the library mostly, and every programming language provides you this a hash table. Okay, hash table, dictionary, map, these are the names of the same one, and array with the string indexes in case of JavaScript. All right, so for each word in the files, you will basically iterate through the file. For each word in the file, check if it exists in the hash table. If it doesn't, you add it there. If it does not exist, you add in the hash table, put the value as 1, and then increase the frequency by 1. Okay, you increase the frequency of this hash table by 1 in case the word is already existing. Is the approach clear? I think everybody has hinted on this approach, right? When no more words are left in the file, just print the hash table, because uh, if a word is already existing in the dictionary, we are just increasing the counter, right? Therefore, this, by the end of all the files finishing, we will have all the word counts. Any questions at this approach? Now, question to all of you is there a problem in this approach? What are the shortcomings in this approach? Yes? What do you think it would be? I mean, what do you think it will block this kind of approach? Okay, time taking, okay, is sequential, resource consuming, memory and time, memory limit, can good. Thank you, Thomas. So yes, thank you, Manjunath. All right, thank you, Nada. Yes. So the problem with this approach is it cannot process the data. It cannot process the data beyond RAM size, beyond your memory, because hash table stays in the memory. And when it stays in the memory, if the memory gets full, it doesn't work, right? It'll say memory full, cannot allocate anymore, and so on. So the memory is a very precious resource in the CPU, in the computer, because memory is limited, okay, is fairly costly, is limited, and and memory you cannot have, I mean, at most I have used 200 gigabyte even in the very high-end systems. And in a typical scenarios, the hash table consumes 4 times the memory than the actual data, because it contains pointers, it has the overhead of various things. So in general, the dictionary contains 4 times the actual data. So the memory will become the bottleneck, right? Now, let's talk about another approach. So somebody suggested in the class that we can actually group the data. And that's a very good approach, by the way. We can break the books into one word per line, right? And then insert each line into the table, right? Such that there is a table with single column, the table with single column containing each word. Okay, is this approach clear to everyone? And once you have this table in the database, which contains a single column of each word, and if you say group by there, if you say select word comma count star from the table group by word, do you think you're going to get the word count in this file? Yes. All right. So Thomas says that it will take a long time. So a long time with respect to what? So do you think it'll take long time to translate the data into one column? That's correct, actually. Yes. So so there is one approach. I'm going to, yes, the yeah. So it will take time in both. One, moving the data from the file system into the database. Second time will be taken while we do the grouping. But the good news is the memory will not overflow. Yes. Okay. But the good news is the memory will not overflow. Why will it not overflow? Because in grouping, there is sorting, and the sorting in the databases is very well implemented such that sorting is happening partly in the memory, partly in the disk. Okay. So most of the databases are heavily tuned not to overflow the memory, but they will read the disk like crazy. They will read the disk again and again. All right, thank you, Ali. Now, the third approach is something those who are coming from Unix background would, connect with. All right, those who are coming from Unix background will connect with. Okay. And I would like to demonstrate this part to all of you during the class itself. All right. So the third approach here, what you see, I'm going to first log in. I'm not logged in yet. All right. Let me log in into my lab. You can actually log in directly to CloudX Lab as well. All right, so I'm here. So I'm going to go step by step into the approach. First thing I'm going to do is cat. What was the file name? Let's say the file name is big.txt. Since it's a huge file, let me just put more. More converts it into page-wise. Okay. Again, those who don't remember our previous discussion, here cat big.txt displays the file on the screen. Pipe means the output, instead of going to screen, it will go to the command on the right, which means the output of cat command will go to more. And what does more do? More displays the page wise. You see more here? Yeah. So you can basically press a space bar and go ahead. Okay. So in case you don't have this file locally, and you want to have a look at it, you can, kind of Hadoop fs copy to local data mr word count and input slash big.txt. Okay, so it already exists for me. So yeah, now here, make sure that you delete this file later on, because little huge file and we will be unnecessarily wasting the space. Okay, so I am going to, yeah, it's not really required what I'm going to do, but if you want, you can try it out. All right, so here is the file. Yeah, this is the file. It basically nothing but the Arthur Conan Doyle's, all the Sherlock Holmes novels are concatenated together, and some more junk data I've concatenated together. Now, there is a command in Unix called sed. What sed does is it replaces one character with something else using the console. Okay, so you can see that SED, whatever data it will get from the input, which means from the cat, it will replace that with something else. All right, let me show you. Let's say I have echo hi Sandeep. Okay, and then I say substitute E with capital E globally. Okay, so you can see that it has converted that into capital E. All right. Or if I want to just say A, E, I, O, U, and I want to just replace vowels by underscore. Okay, so you can see that, but it has not made changes anyway, just given us the output. Is everybody with me on this? Yeah. So the output of echo, instead of coming to us, it went to SED. SED substituted the characters with something else. Okay. Now, similar way, we are going to substitute in the big.txt. We are going to say substitute new line, sorry, space with new line globally. And then let's take a look at page-wise. The last character stands for the options. Like when you say Control F, okay, when you say Control F, you have three things, right? Three things. First one is what to replace with what, and what are the options, right? Similarly here, first this is the first text that we are substituting this with this globally, meaning don't replace it once, replace every occurrence. All right, now you can take a look at this. So you can see it is now kind of cleaned. Sorry, it is not cleaned. It is basically we replaced space with new line. Correct? We replaced space with new line. Okay. Next thing we are going to do is we are going to give this to the sort command. Okay, and take a look at it. You can see that sort takes decent amount of time, and it has put space at the top. Okay. Wow, there are many empty lines. Okay, there are quite a few empty lines in this file. Okay. Now, sort command ordered these words given by SCD. So the output of cat, which was just printing the data found in big.txt, went to SCD. Output of SCD went to sort command, and then we printed it page wise. Okay, why am I wasting your time on this? Because anybody, whether data engineer, whether software development manager, or data scientist, data analyst, anybody who works extensively on data, they cannot live without working on Unix pipeline. This is the pipeline uh, that used to be there traditionally. Okay, so that's why I want to make you aware of these commands, and I leave up to you to go through these commands in detail. Try to use these because this is your first step into data engineering. Okay, and good part is that we can use the same tools and commands inside Hadoop and Spark. All right. Therefore, this is integral part of data cleaning. All right. And you will see that your performance, efficiency, some of you might be competing at Kaggle, or some of you might be appearing for various kinds of tests. If you tell them that you could use a Unix command to do this, and this generally leaves a great impression. So it's very important to learn this kind of pipeline. All right. A lot of you might disagree with me, but my experience says that understanding of Unix command pipeline pays you in a long run. All right. So this is a very basic work. Now, next thing I want to explain to you something called unique minus C. All right. Let's say I'm going to show you something. Echo hi, and then I'm going to say echo hello, and I'm going to say echo hello, and again I'm going to say echo hi. All right, so it has basically printed, let me make this window a little different because it's cutting the corners. All right, can you see now? Okay, okay, so here, yeah, now you can see I've just printed hi, hello, hello, and hi. Now let's say I want to pass this to WC. So WC shows that, okay, not like this. I will group all of this output into one by putting brackets and then run WC. Okay, so you can see that WC has printed. There are 4 lines, right? 4 lines, 4 words, and 18 characters, right? Now, if I put my unique command, so you can see that hello has been eliminated from twice to once, but hi is not. Why so? Because there is a unique this command called unique in Unix. It assumes that the input data is ordered. It assumes that input data is ordered. Okay, unique minus C prints frequencies in the ordered data. Okay, so what does unique minus C does? It prints the frequencies of the words if the data is ordered. Now we are ready to apply this logic in what we were trying to do. Now we could say unique minus C, and again I'm putting it pairwise. Yes, it does print distinct words. So this is what it has done. Okay, for each word it has computed frequencies. And since there are so many numerics, and I'll have to jump ahead and see, you can see that absurd has occurred 14 times, absurd comma, and all of this, right? Okay, so those who are interested can try this command. All right, now if let's say we want to clear up everything that is not there, we say not A to Z, okay, or 0 to 9, substitute it with nothing and then pass. Okay, so you can see that. All right, now the data is cleaned. Or let's say you want to do a further work, translate A to Z, sorry, capital A to Z into small a to Z. All right. Now let's take a look at it. So I'm trying to demonstrate to you how things become very simple using the Unix cell, and we will try to do the same thing using Hadoop command. Okay, now this time you can see that where is that word ABS? You see, absurd has occurred only once, but 24 times. Okay, I hope I have not confused all of you. Let me send you the command. All right. So in this command, you can see first we printed the cat command read the data from big.txt file, meaning disk, and gave to this command. What it did, replaced space with new line such that each line contains only one word, right? Then we substituted anything which is not A to Z or 0 to 9. If it's not A to Z or 0 to 9, substitute it with nothing, meaning delete it, and then translate capitals into smalls, that is TR command. TR command translates the capitals into smalls, and then sort, and then unique. Is everybody with me? Prashant's question is, shouldn't we also have A to Z while substituting? Oh, that's correct. Thank you. Thank you so much. Yeah, actually, he is very right. So, yes. So, there is a mistake in this. Thank you, Prashant. Yes, it's a very good point. Let me fix it. So, instead of that, what we could do is first translate capital to lower and then use this. Okay. Now, good. Now, So, I mean, those who are confused, I'm again writing it here. So this portion, who can tell me what it does quickly? Yes, displays the content of the file. And this portion, yes. And this portion, yes. Good, good. To lowercase. This portion, so, okay. What does this portion call? Let's say 1, 2, 3, 4. Yes, remove. Yes, correct. And what does this fifth portion do? And this portion? All right. And of course, this portion. Good. Wonderful. Now, out of these, out of these 7 commands that we have used, these are the 7 separate programs that we have chained together in order to achieve what we are trying to do. Now, out of these 7 programs, which one do you think will consume maximum amount of CPU and memory? Maximum amount of CPU and memory is consumed by who? Okay, okay. So, all right. So, question is right now. Uh, Question is whether unique or sort. Sort, of course, right? So, I'll give you a reason because so this is the most important aspect. This guy is the sort command is going to be the bottleneck. Okay, because sort is the only command which is memory intensive as well as CPU intensive. All right, but unique is pretty straightforward. I'll show you why. Imagine that we have this data which is already ordered. Now we have to compute unique. So all we have to do is keep going from top. Okay, in case the next one is different from the previous one, okay, just increase the counter. If next one is, sorry, in case next one is same as the previous one, increase the counter, which means 1 is twice, so 2, then 3. Now will it simply print 1 space 3, correct? Then it encountered 2, it did not print anything. Then it encountered 3. The moment it encountered 3, it will print 2 has been occurred once, and then it'll do the rest. Okay, so it doesn't keep anything in memory. As and when the data is coming in, it will only retaining 2 numbers, to one string and one number. That's all. So unique command is not the bottleneck. Okay, is everybody clear why unique command is not a bottleneck? Because unique only works on ordered data. It assumes the data is ordered, and all it does is goes from top to bottom as in where the data is coming. It retains only the current running word. That's all. It doesn't retain the entire thing. All right. So now question is that the sort command is kind of kind of the bottleneck. Okay, let me give all of you the sort command here. Okay, so this command which I did here, I think I've given this one to everybody. All right, so here we go. All right, this is the most practical way of churning data. Okay, yes, I've kept it in file. Thank you, Sundar. Yes, it is here. All right. Okay, I will also copy the other parts. All right, this. So these are the two commands I executed just to demonstrate you that this command actually work. Now question is that this command will again overflow the memory called sort, right? Sort command will overflow the memory. All right, now in this, the question is, if let's say you have limited memory, luckily the sort command also comes with disk-based sorting. Okay, so if you see in the manual of man sort, any command you can find their manual by typing man sed, man cat, man tr, or man sort. Okay, so you can see that there are all kinds of the all kinds of options. Now here, there are quite a few interesting options in sort command. One of those, one of the commands is parallel. Okay, parallel means using many processors, it can sort the data. Second, it can basically, I will show you some more things in this. It can basically utilize only a part of memory. Okay, so all right, I will show you. Yeah, minus s means it will only consume that much of RAM. In case, let's say your data is of 100 gigabyte and you want to use, or let's say your data is say 15 gigabyte. Okay, data is 15 gigabyte and you have to use sort command, you can basically say that use this much of memory. So while using sort, you could say minus capital S 1 gigabyte. So it will only use up to 1 gigabyte. Okay. I hope everybody is with me on this so far. Great, wonderful, wonderful. And yes, this is important because this is something I have used in past. Okay, and this was my savior at a lot of places. This sort minus s 1 gigabyte. Okay, all right. Now we talked about three separate approaches, and third approach, we just to explain the approach, we went through the entire Unix pipelining. And the only way to learn all of this is by trying again and again, go through the manual, try various kinds of data. Now, okay, so we could also use this approach. So we talked about first approach, which was memory issue. The second was the issue, second was the SQL way. Third was the Unix way. In Unix, we are using only 1 GB of buffer to make sure that we do not consume too much memory so that we do not overflow the RAM. Okay. Now, question to all of you is that in the approaches second and third, in second we had SQL and third we had Unix. All right. Now, can anybody, yeah, answer this? What kind of problem do you see in SQL and Unix approaches? The approach number 2 and approach number 3. What kind of problem do you see in this? So yes, Mohit, for sorting minus S, we are utilizing the disk, correct? Sort minus S utilizes the disk. Basically, it splits the buffer into 1 GB size, orders that, and then merges the result. Correct, Jamil? Okay. Yes. Thank you, Priya. So exactly the problem. Thank you, Jamil and Saptrishi. Yes. So in approach 2, if you have to do this again and again, then you might go for indexing. If you just have to do once, you don't require indexing because indexing would take the same amount of time as grouping will take for the first time. All right. So yes, the approach number 2 and 3, SQL and Unix, they suffer from these three bottlenecks: CPU, disk speed, and disk space. All right. So first problem would be the disk speed, because the time that it takes to read the data from disk is generally more than it takes to sort the data. Therefore, for example, it takes a longer time to load the data into the RAM. If you see the numbers, you will numbers of the disk speed. So first thing that will become the bottleneck is disk speed. It's and then CPU and then disk space. Okay. Now, what is the alternative? So I'm talking in terms of we started with a very primitive approach. The primitive approach was using a hash table. The problem with hash table was that hash table cannot be made distributed, cannot be kept in the disk. It has to be kept in the memory, and the memory was the bottleneck. And then we moved to the second approach, SQL, and third approach, Unix. In second and third, the memory was no longer the bottleneck, but the disk speed and the CPU and the disk space would become the bottleneck. Right now, what to do in case the data keeps on becoming bigger, right? So first approach is okay till you have say 1 GB of data. Second and third approach is okay till you have say kind of 100 GB up to 100 GB. But when the data starts going beyond 100 GB, then the disk speed and CPU and disk space will become the bottleneck, right? Because uh, it takes a long time to write to the disk, because every time, so the way this approach works is it breaks down the file into small parts of 1 GB, the sort command basically, and then it tries to order the data in that one particular that part, and then tries to sort it and then merge it. So when it tries to sort individual part and save it to the disk, it is going to take a long time. So every part need to be saved to the disk and then read from the disk. So uh, writing that amount of data, first reading, then writing, and then again reading, so that many times. So twice reading, once writing, of that same data. So if you have 100 gigabyte data, so total amount of reads will be twice 200 gigabyte, and writes will be 100 gigabytes. That means it's going to take a long time. All right. So even if you parallelize the entire system, the writes will take a long time. And also, uh, I mean, reads cannot be made parallel. Similarly, writes cannot be made parallel if it's a single disk. If you have multiple disks, you can still hope to parallelize the disk writing. Good. Now, what next? What can we do? So in before Hadoop came into play, and we were working at we were working at the we were working at say at DShare, the strategy that we followed was something of this sort. Okay, before I jump into this approach, let me answer um, Mohit's question. Why would CPU become the bottleneck? Let's say the data is goes beyond 15 gigabyte into something more, right? So you will have to kind of order this data, and you when you order the data, number of comparisons are equal to number of elements into logarithm of that number. And if you see, the CPU is going to going to spin uh, a lot. Okay, and therefore the CPU might also become the data. In case, let's say, you have tried to improve disk speed. Let's say what you did was you used SSD, you used some other strategy for the disk. Okay, then the CPU might become the bottleneck. Do I make sense to you? All right. So what we used to do is we basically kept like multiple machines parallelly. And from one machine called launcher, we will send the data to both the machines, machine 1 and machine 2. We send the data, let's say there was a huge file, sa, re, re, these three lines we send to machine 1, and machine 2 we send to ga, ga, re. This is the input to both the machines. So we have three machines, launcher, machine 1, machine 2, and both these machine 1 or machine 2 are ordering the data using, say, any of these approaches. Okay, and then let these machines work in parallel and give the result. Okay, and give the results, and then launcher will merge this result into something meaningful. Okay, you can see that machine 1 and machine 2 has merged the data. Ray to Sa1 has come from first one, meaning Ray has occurred twice, Sa has occurred once, and machine 2 has given Ga2 and Ray 1, and then launcher had just merged. So this is just one approach where the merging is happening at the launcher. But remember, both machine 1 and machine 2 were giving the data in ordered way. Okay, in ordered way. Now, when you get the data in ordered way, it's very easy to merge those, right? It's very easy to merge those. I'll try to demonstrate this because this is a core interesting part as part of the distributed sorting. Okay, this is called an external sort, and we used to use this earlier. Okay, before Hadoop and other frameworks were in place. All right. So how does this system merge these results? It's pretty straightforward. Imagine that there are two streams of data or two array. Okay. Both are ordered 1, 2, 4, 5, 10, 11, right? And then you have 2, 2, 3, 3, 4, 4, 4, 7, 19, and 100. Let's say machine 1 gave us this result. Machine 2 gave us this result. Merging these two is very straightforward. Okay, I'm trying to give you example of how merging is so simple if the data is ordered. If the data is ordered, merging is extremely simple. Okay, all merger has the merger has to do is pick up the head, compare the two, pick up the smaller one, and put it in the output. Okay, now pick up the head. Okay, if both are equal, pick both, put it in the output. Okay, then compare the head, pick up the smaller one, put it in the output. Compare the head, pick up the smaller ones, and put it in the output. Compare the head, pick up, and put it in the output. Good? Yes. Next is we compare 5 and 7. So 5 goes here. And then we have out of 10 and 7, 7. So it keeps on comparing the heads of both the results given by the two machines, and it can do it in the real time. Okay, so this is the way a comparison typically happens. So it does not really have to maintain the entire stream in the memory. It can do it as and when the data is being read. Okay, so this merging happens in that way. So it will basically compare Ra with Ga. Since Ga is smaller, Ga goes to the output. Then Ray with Ray, that means Ray goes into the output after summation. Okay, and then Sa. All right, is the approach clear to everybody? Okay, okay, okay. I still don't see 26 Ys. All right. So this is generally called external sort, meaning sorting the data using an external machine. Okay. So, and this was like a traditional approach we used to do. The launcher would send the data to machine 1 and machine 2 or machine 3, machine 4, and then launcher will merge those. Also, those who are inclined to understand how would multiple, how would you merge data from more than two machines? Okay, more than two machines. Quick answer is take a look at min heap, okay, or max heap. Right, it'll basically retain the min or max heap from of the heads to find out the minimum of those numbers. All right, so take a look at this in case you are more inclined, because this is the very kind of bad question of people at Amazon or Google or say Microsoft or Oracle to ask this kind of question, that how would you utilize 15-20 machines to order the data? Okay, all right, so now this is okay, so yes, Saptrishi, external and distributed sort mean the same thing. Yes. Now the approach number 4 looks very decent, but there are problems with approach number 4. What do you think are those problems? Correct. Thank you, Sundar. Yes, network is one such problem. Yes. Failover is another problem. Thank you, Saptarshi. Wonderful. Yes. So failover is another problem. Any other? So in this approach, the approach number 4, whereby we send our data in parts to many machines and then merge it together to give the results. Okay, good. So this first next question is high availability data synchronization issues. Thank you, Ted. And Kushi's question point is need to send sorted data. Yes. Yes. Thank you, Thomas. We'll have to wait for the slowest machine. Although you can start merging whatever streams are available, and then merging can be can further happen with the slowest machine. Okay. Mishra's question is point is the merging is not distributed. Very good. Very good. Okay. I'm actually generally happy with my class because when I ask these questions to even the instructors, they are not able to come up with, because I'm trying to hire some more instructors for my uh, hiring, and when I give these kind of questions to them, most of the instructors themselves do not know. Okay, so great, great, wonderful, because these are the heart and the backbone of distributed computing. Okay, because, and if you see as we go forward, whether you use Spark, Cassandra, MongoDB, or anything, the general ideas like how do you distribute the logic, you like for example we talked about yarn, we talked about the Hadoop 1.0, we talked about the zookeeper way of elections, and then we talked about HDFS, um, and we also talked about MapReduce, this kind of models. These theory, this part is kind of something, no matter what frameworks come into play, they're going to use similar basic principles. All right, we also will go into what is CAP theorem and others after a while. All right, so yes. So Priya's point is that we need an application to collect data, know the data is clean, and then perform the computing. And here the merge. Yes. All right. So So yes, now the problem with fourth approach, you have already told that transport of the data is going to take long time. For each requirement, we would need to create special purpose network oriented program. And therefore it would require a lot of engineering like synchronization issues. We have to wait for slowest machine, and we'll have to take care of in case one machine goes down. We will have to okay, there was one more answer which I'm missing here. There was one more answer I'm missing. High availability is the right word. So because of these reasons, we use the we use the MapReduce. Okay, we use the MapReduce. Now, all right, wonderful. So these are the reasons why we use MapReduce. Okay, a question from Arsalan is, I do not have correct example, but hypothetically asking this question, assume we have to take an average of few records and these are on two different machines. Good, then we'll have to use average function on few records on machine A and then same on machine B, and then after merging again average function to gain the final result. Don't you think it'll give the wrong result as compared to do the same function in one time? Very good point, Arslan. And yes, and interestingly, these are the real use case and these are the real problems because of which we fail to distribute. Okay, therefore our intelligence is to convert a problem into a problem that can be distributed, right? Say for example, let's take your case where we are trying to just compute the average, right? Average of average Average of the two parts is not equal to average of the whole, right? It's not always. Therefore, as Mohit suggests, that we compute the sum, not the average distributed way. We compute counts and sum in the distributed fashion, and then on the node where we are collecting all of this, on the launcher, we divide. And that's a strategy we will keep on following again and again. And there will be problems that you cannot distribute. There will be problems that you cannot distribute. Okay, I will also go through those kind of problems. Right. Great, great. Keep these kind of questions coming so that we all are understanding what we are right now studying. Ali's question is, it's too complicated and there is always a new use case which needs a new solution. Okay, so yes, sometimes the problem looks fairly complex, okay, but you can generally break it down. Okay, so I will give you a good thumb rule as we will follow further. So the general work where shuffling is not required, like, okay, like for example, we were trying to sort it, keep a hash table. So the general strategy is, if there is a shuffling required somewhere, try to convert the problem into sorting problem. Try to make it like a sorting problem and distribute the sorting work on multiple machines. And rest of the things you can do it on a single machine. Okay, so yeah, so as we proceed further, the good news is that most of the complicated work, like um, SQL commands, they don't need to be coded in Java or MapReduce, but the other complex problems, other kind of problems would require a little bit of thoughts. Okay, so we will go into more details as we proceed further. All right, it won't be too complicated as you practice along. Okay, so that's the uh, you know but the concern is real that it might go fairly complicated, but if you practice as we go forward, you will find that yes, you are able to convert a problem into distributed. And for example, there are lots of problems, real use case, that you really cannot um, cannot convert. Okay, so this was our foundation on MapReduce. And interestingly, this approach is what MapReduce does. Okay, in a distributed and nice fashion. Yes, let's take a break for 10 minutes. Back by 9:45 p.m. IST. Hi everyone, I'm back. So should we start now? Yep. All right. All right. So before the break, we established why should we be using MapReduce. Uh, okay. So MapReduce is nothing but approach number 4, customized, as in what has to be executed on machine 1, machine 2, and the launcher that can be customized. Okay. That's what is MapReduce. So again, MapReduce is a paradigm in which you create two functions. One is called mapper, other is called reducer. Mapper converts input data into key and value, and reducer aggregates all the values of a key. Reducer is optional. Mapper could be very simple, as in whatever input it reads, it just prints the same thing. Okay. And so that's the general paradigm. And using these two functions, you can achieve a lot of kind of, you can achieve solutions to many kind of problems. So you can chain one mapper reducer couple with another and so on. So mapper reducer go as a pair. Reducer may or may not be there. You can skip reducer, but and you can chain them together, chain multiple MapReduce pairs together. All right. So one MapReduce job contains mapper, optionally reducer, and MapReduce jobs can be chained. All right. Now, it is also supported by many systems like MongoDB, CouchDB, Cassandra, and now using Spark as well. Okay, in Spark, mapper and reducer, it doesn't exist in the pair. They can individually be many times. All right, so that's the benefit of Spark. And mapper and reducers in Hadoop can be written in Java, Shell, Python, or any binary. Okay, so here is an example. Let's just talk about a very simple processing. Imagine that you have to convert an image into 100 by 100 pixels. Okay, let's say you have a directory of profile pictures. Let's say, okay, let me give more context. You work at Facebook and there are billions of profile pictures of people. You want to resize them such that the everybody's profile pic is only 100 by 100 pixels. Okay, is problem statement clear? Now, since there are there are billions of profiles, so there would be billions of images, and using a single computer is definitely not possible, no matter whether it's supercomputer or whatever mechanism. So in these cases, you could do a few things, like you could write your own program which will resize it on many machines, but again you will stuck in the same scenario as we have described. Instead, you could use MapReduce. Okay, so the way MapReduce will work is you will write a program which takes an image as the input and converts that into another 100 by 100 pixel. Your individual program, the logic, does not need to know about the location of the data. Okay, it all it has to do is just translate it. All right. Now you will hand over this program to Hadoop in the form of mapper. You tell them that, hey, this program is my mapper command. You tell Hadoop that this is my mapper command, and we don't have reducer. Now, what Hadoop will do while executing this map reduce job, which contains only mapper with this logic will get executed against every file. Okay, let me take a step back. So this folder would be distributed on HDFS because some file would be on one machine, some file will be another machine, and so on. Okay, so this folder is distributed in the sense like if there is a bigger file and that is beyond 128 MB, that'll be on two machines. And in this case, that file will be brought to one machine. But mostly, this mapper logic will be executed nearer to your data. Mapper logic will be executed closer to where your data node is having the file. Okay, so all the data nodes that will that contain these files, that list will be gathered by MapReduce job, and that list will be out of that list of all the data nodes that it, it will be found out by Yarn that these machines are free, and your mapper logic will be executed on those machines. Now, some of you must be wondering what happened in case of Yarn. So this logic of MapReduce is staying in your in the app master. Okay, so app master will tell Yarn that can you get us all the nodes which are nearer to this folder and execute this mapper on all those nodes. And once done, save the result in HDFS. Okay? Now, Thomas' question is, how do you define near data? Physically near. Yes, that's how. So since HDFS knows that where is my data, right? Because in Hadoop, we specify the entire tree. This is called data locality. We will talk about data locality again. So data locality means Hadoop knows about the entire nodes based on the IP address, and we also can configure that. So based on that, it forms the entire network as a tree and knows that which machines are closer to each other and so on. Okay, so the first preference of executing mapper is on that machine, the same machine which contains data, right? Yes, Yarn's job is to find the nearest data. Okay. So Sundar's question is, in case of images, each image will be on one machine. So since image is not generally 128 MB, it will be on, it won't be broken. So each image will have single block. Okay, next question from Ali. How is data distributed? SDFS distributes a big file, but we have a lot of small files. Yes. So since we have a lot of small files, some files will be in one node, some files will be another, some files will be another, and so on. So if you have 10 nodes, the chances are the files would be uniformly distributed. Okay. So if you have 10 nodes, or let's say you have 1,000 nodes in case of Facebook, these files will be distributed on those 1,000 nodes, and your mapper logic will be taken to those nodes which contains the actual file or replica, because there will be three copies. So any of the node, whichever is free, Yarn will find it for you and execute your mapper logic inside the container on all those nodes. And then the result will be saved in the HDFS, which means on the same node itself. correct, using the data node, it will basically first copy generally goes to the same node. So in effect, there is no transfer of the data. There is no transfer of the data on the same node. The data is getting translated, the image is getting translated. No transfer across the network is happening. This is the magic. So we got two things, two advantages. One, no network transfer. Second, our work got distributed on thousands of machines. So these two big advantages, as we told earlier, that discrete speed, CPU, and network speed, they were the bottlenecks. And this mapper reduced logic basically converted that into alleviated those pain points. No network transfer, and the work got distributed. All right. So this is a simple use case, not the word count. Okay, it's good to be confused, honestly, because that gives a sign that I haven't explained things properly. Okay, Priya says, consider some reason image is greater than 128 MB. Will this be divided? But that doesn't make sense how it is handled. Thank you, Priya, for that question. So that's where in this diagram, okay, in this diagram that you see, before consumption, of raw data block from HDFS, the data is translated into something called input format. We will talk about input format again. In the input format, we basically convert the raw data, raw block, into some meaningful records. Okay, and this translation is something we'll have to be careful. We'll have to use the correct input split type. If we are dealing with the whole file, mention that we want to tell Hadoop that, hey, we want to consume the whole file. Don't break it into record. Otherwise, it will break the data into one line per program. Okay, do I make sense, Priya? Okay, so basically the logic, there is a layer between mapper and the HDFS. That layer of logic, the libraries, there are many libraries available which translate the raw data block into back into something meaningful. Okay, something meaningful, and that's called input format. We use input format for that. Okay, a question from, okay, so I hope Ali, you got the answer. Yes, Saptarishi, go ahead with your question. Jin's question is, who splits data file in the Hadoop and when the data being splitted? So data has been splitted by name node data nodes, you remember? So the splitting happens by HDFS command. Like Hadoop FS basically splits data and stores it in the data nodes. Okay. Thomas' question is, we have always enough buffer on the nodes. Enough buffer on the nodes. Mm, I did not get your question, Thomas. You mean the memory? Ted's question is, so the app master then stores the mapper results into the HDFS machine? Yes. So it's not app master, it's a container that directly is storing in the HDFS. Okay. So basically, app master informs the container that run this logic, and the result should be stored in the data node. Okay. So that label, all right, I hope I have answered your question. So Thomas's question is, he computes only parts of big image. Okay, so it's up to us. Sometimes we may want to consume the entire image, as in this case. Sometimes we may want to consume, say, parts of this image, right? So it's up to us which input format we use, and then accordingly, our logic will be executed against either the entire image or parts of the image. We will talk about how the raw data block get transformed into something meaningful. Okay, a question from Kush. If image is greater than 128 MB, then we should have high size data block by default. Not necessarily. Okay. Okay, so we don't. So there are strategies whereby only slight data will be transformed, and we will talk about those strategies a while later. Very good questions. Thank you, Saptarisi, for that question. Question is, as I have again and again iterated since the beginning, this logic of mapper is going to get executed near the data, meaning on the data nodes, meaning containers in the yarn will be created nearer to the data. Okay, question is, that means all data nodes will have containers. So ideally, yes, but sometimes we do not want certain containers to be executed on all the nodes. So some nodes we just want to keep it as for the storage. In those cases, since the same data blocks will have two more copies somewhere else, in those cases, it'll be executed there. Or nearer to the data in the topology of the network, whichever node is nearer to your data, it'll find it will create the container on that and execute the logic. Okay. So did I make sense to you, Saptrishina? So find the free container nearer to the data. First, it would try on any of the nodes that are free and containing the replica of your data. If it's not found, then the node which is free and available nearer to those data nodes that contain data. All right. Kush's question is, I can't get how to resize if we split image into blocks. Good. Let me try to say this. So what happens, let's say your mapper, let me try to answer Kush's question. Let's say your file is divided into 3 blocks. Okay, 2 blocks are on one machine. And when your mapper, when we are executing logic, so what all the things we passed to MapReduce so far? One, the directory which contains our data. So I'll just note it down. Okay. So what is it that we pass to the MapReduce? Args of MapReduce. Okay. First one is the input data storage, data folder / file. This is one thing which we pass. Then logic of mapper. Okay. Either Java code or binary. Okay. The way we passed WC last time. word count. The third is the third is the input formatter. Okay, that converts raw data into meaningful objects. Okay, and these objects become the input to your mapper. Okay, input formatter. Okay, input formatter. Okay, input formatter converts the input image into something meaningful. Now, for this conversion, it might have to transfer the third block or remaining part from another machine to this machine. Okay, it might have to transfer in the cases if you really want to load the entire file, which is distributed on 3 machines. It contains 3 blocks, so it is on the 3 machines. So in those cases, it might have to bring it back to one node. Therefore, we are very careful about how we structure our loading of the data. Okay, that's why we provide correct input format and organize our data accordingly. Okay, so for example, let's say we are trying to compress the data. We don't compress it using, say, usual zip, because if you compress your data using usual zip, all the parts, whenever you would require all the blocks of your data, whenever, let's say, there was a humongous file of 10 gigabyte, you compressed it and it became 8 gigabyte. Every time you have to access the file, right? Every time you need zip file, you need all the parts, right? And therefore you'll have to bring it back to the single node and then use it. Correct? So so we have to be cautious. We have to be cautious as in how we are storing our data. Therefore, let's say for compression, we will not use zip format. Instead, we will use the format of compression provided by HDFS. Okay, do I make sense, Kush? All right. Okay, so there we go. Saptrishi, his question is, my assumption was only primary data file is used always. What is primary data file? You mean the first block of your replica? No, it can be any. HDFS doesn't differentiate between primary block or replica block. All the three are just a copy of the same file, same block. All right. A question from Thomas is, do we always have enough disk size to store the converted image on the same machine as the input image without data transfer? As you started, very good question. Very good question. And yes, let me try to answer it. Okay. Yes. All right. One thing which I have told here, one thing which I have told here is that the mapper is going to store the output into HDFS. And the general strategy is it will copy the first block onto the same node where you are located. Okay, what does it mean? Let me try to explain this. Right now, we are on this particular node called e.cloudxlab. If I say Hadoop FS copy from local, okay, which means I'm trying to write the data to HDFS from local file, correct? So the standard strategy of Hadoop is that the first copy of your data will stay on the data node that is running on this machine called e.cloudxlab. This is called data placement policy. HDFS provides something called data placement policy. If you and people have been customizing it. So the default strategy is when you are copying data to HDFS from within the network, it will copy, it will try to copy on the same machine. In case the same machine is full or it doesn't have storage left, then it will transfer the data to some other machine. All right. So take a look at something called data placement policy. All right. Wonderful set of questions. Did it make sense to others as well? It's a very important question. All right. A question from, okay, these two questions, let me take a quick look at those. A question from Manjunath. If the output file is greater than, so the file is divided and stored across two different nodes. Yes, that's correct. So not necessarily the two blocks of a file are going to be on different machines. Okay, two replicas are going to be on different machines, but not two blocks of a file. Okay, and did it make sense to you, Manjunath? Question from Kush. Does block strategy applicable for HDFS output as well? Yes. Okay, good. Both of you have answered the same, asked the same question at the same time. Jing Yan's question is, can you show an example of a splitting of large image files to different nodes? Okay, I don't have example data. Last time I tried to show you something. So in Hue, in the dataset folder, there was a CSV file, which was copied there. Okay, so I don't have an example where I have an image which is bigger than 128 MB. Okay, if you have an image, you can basically upload it via Hue or using SCP by yourself, and then take a look at the blocks using HDFS command. Okay, HDFS FSCK command. Try uploading it into Hue, and you will see. Okay. So Nada's question is how HDFS will store output when different machines required. So in the same way, just like we are copying data from local, so container will be running on say A.cloudxlab, B.cloudxlab, C.cloudxlab, or E.cloudxlab, F, G, H. And on that machine, it's like a process running on that machine. Okay. So when it saves the output, it'll basically be saving into HDFS, and then it will let Hadoop decide using the standard policy. Okay. Just like when I copy data from my machine called e.cloudxlab, if I copy data from this node into HDFS, it might go to the local if the local is free, or it might go to some other node if that is free. Okay. Question from Kush is, how long does HDFS retain output? It retains for forever. It doesn't delete it unless you ask it to. Okay. All right. So great set of questions. All right. Yes, of course, it can be reused. And that's how the chaining of job happen. First job saves the output in HDFS, and then second job pick the output, process it, and then again saves it, saves its output into HDFS. And that's how Hadoop's previously before Spark, that's how people chained the job together. All right. Good. Now, so far in our example of image resizing, we were only having mapper because there was no shuffling required. The operation was very linear. Data in, translated, and data out, right? There was no such requirement like find the minimum, find the most beautiful image out of all, or there was no such requirement like find the most bright image or to find the image with the maximum green color in it. Okay, so there was no intercommunication between the nodes, right? And it was fine. We did not have to use the reducer phase. If let's say, if let's say you come up with the idea that let's find out the greenest picture, the picture which is most green in color, in those cases you will have to kind of shuffle the data, merge the data from all the nodes, and that's where the real power of MapReduce comes into play. Okay, so you write two parts of logic, one is called mapper, other is called reducer. Okay, and then this mapper will translate the input into key and value. Okay, and based on this key, the data will be grouped by Hadoop. Hadoop will do the grouping. You will only specify the key of grouping in mapper, and then in the reducer you will decide what to do with the grouped data. For each group, for each group, your reducer logic will be called. Okay, for each group, your reducer logic will be called. So let's take a look at it. Let's talk about counting the word frequency. Okay, so if you remember our SQL query, all we did was select count star, group by word, right? Similarly, here what we are trying to do is the same thing. We are in the mapper, this is our mapper logic. What this mapper does is it basically converts each line into many key values where every word is a key and value is just anything which we can count later. Okay, value is just one here. You could have X, you could have Y, anything which you can count later. So let's say you had an HDFS file which has two lines, sa, re, sa, ga, that gets translated into sa1, re1, sa1, ga1. Okay, so your mapper logic has converted it into key value pairs. Okay, it has converted it into key value pairs. And then the output of mapper is ordered and grouped by Hadoop. Okay, it has been ordered and grouped by Hadoop. Every every output here, every output of your mapper command is going to get sorted on every machine. You can see on every machine the sorting is happening. here. Okay, once the data gets sorted on every machine, merging it is very easy. So this output of your program, Savan, Raven, Savan, Gavan, get ordered and sorted by the way of distributed sort. Okay, Gavan, Raven, Sa 1, comma 1. And the reducer logic here, okay, reducer logic basically is given two things by Hadoop. One is the group, the word on which the data has been grouped, and the array of frequency. So Sa is the first argument, the list is second, and then your reducer can operate upon it, whether it wants to compute average or sum or something else. Okay, so a question from Saptrishi is that mapper has to write sorting? No. Sorting is a heavyweight lifting, and that's why Hadoop basically flaunts its sorting skills. And you use Hadoop for actually sorting data, mostly other than executing data on every machine. All right. So if you think about Hadoop in general it's a huge distributed sorting engine in which you can customize on the basis of sorting, the data definition, and so on, right? All right. So this is how the MapReduce works. Let me take one more example. Okay. All right. So Jinyang's question is, so sorting grouping is done by Yarn for mappers output. Yes, it is done by MapReduce application master. So I'll explain again. So if you go back, on every machine, the result of mapper is going to get sorted. This whole thing is running inside container. Okay, this whole thing is running inside container, and application master has given that logic of sorting data on every machine. A question from Manjunath. Assume that we have run the MapReduce code, and if we rerun same MapReduce code, is anything cached in Hadoop? No, nothing gets cached unless you explicitly mention. Okay, only that if you are running exactly same command, you might have to change the output folder because output folder might be existing because of previous command. Okay, so they have a idea called distributed cache. Okay, there is something called distributed cache. So when you send something to Hadoop, Hadoop has to send the same command to every machine, right? Because every machine has to execute the logic, the mapper logic. Let's say you are using some library, some small config file, and so on. That they, when you are handing over your mapper logic to Hadoop or reducer logic, mapper reducer job to Hadoop, you will also hand over, say, config file that are required on the machine, or libraries and etc. to be executed that the library or the data that are needed to execute your mapper. In those cases, it creates something called distributed cache. Distributed cache is a kind of a temporary location whereby it copies your logic, data, etc. on every container, on every node containing container, and then executes it. Okay, so that is something called distributed cache. But that is not same as caching usually. Okay. Good question. So question from Kush is, aren't we overloading reduce? Yes, we are. That's why you can make multiple reduce phases. Okay. One more example of map reduce phase. Let's say there is a city, sorry, there is a country and you have the temperature of every city in this country. Temperature, city, and the date. Okay, you have three details about the temperature. Now, if you have to compute maximum temperature and you want to use MapReduce, what you will do is, for every line in the input, you will only print city, comma, time. So you want to compute maximum temperature of every city. All right. So for this kind of job, what you need is you need to group the data by city and then compute maximum temperature, right? Therefore, in the mapper, you will make the city as the key and the as temperature as the value, okay? And let Hadoop group it together. So you can see NYC 2020, 21, BLR this, and so on. And then again NYC 26. And then you let Hadoop group it. So this dashed line is the work being done by Hadoop MapReduce framework. And the framework is essentially grouping the values based on the first key. Okay. So for each city, you get the list, and then in the reduce, you basically compute the max or min, or let's say, uh, you can do many things here. All right. So this is the usual way of computing max. All right. So question of Kush is that as we discussed, output to reduce should not be sorted. The input to the reduce comes as sorted. Okay. So it's sorted by the data. It looks like that way because of our example, but it'll be sorted here. Okay, let me sort it for you. It doesn't look like sorted, but let me make it sorted. Okay, let me see how easily can I sort it. All right, good. All right, thank you for noticing this. Okay, so yes, the input to reduce is ordered. All right, your reduce function will get executed against every line. Your function gets executed against every line. This is not same as reduce process, because reducer process will be processing many records, but for every record it will be executing this function. Similarly, you will write a mapper function which will consume only one record at a time. Okay, so it got these records, it is split it by comma, and then created three variables and printed only these two. Okay, does it make sense to you? Did this example make sense to you? So Thomas's question is, sort always means sorted and grouped? Not necessarily, but once the data is sorted, grouping is not too much of work. Okay. Once the data is sorted, creating the group is a very straightforward process. Therefore, it goes without saying that sorting or grouping is the same thing. All right. Priya says that, have a basic question. MapReduce works on structured data or on unstructured. It can work on anything as long as you are able to create records out of it, And those records may be big objects, maybe image, maybe anything. If you're able to create records, those record doesn't mean here we call it input split. As long as you are able to create input split with the definition of what is your object to process, you can process it. Whether it's a image, whether it's a relational data, whether it's a XML or a JSON data. All right. A question from Manjunath: is grouping done using hash value of the key? Is grouping done using hash value of the key? No. Okay. It is done on the real value. In case there is a hash collision, it does not mean that those values will also come together. All right. A question from Ted is, for chained mappers, is it always linear or can it fork to other mapper based on certain conditions? So very good question. So question is, if we are chaining mappers, it is always linear. So it is up to us. We can write a complex logic that first execute this. Once that is completed, then check these few conditions and then execute either this job or that job. Okay, so both the things are possible. One is linear way of execution, whereby you define the dependencies between the jobs, between the jobs, and then let them get executed. Okay. A question from Priya: what is the example of where the record cannot be created? If you cannot define a record, it'll be impossible to get it processed. For example, in the previous case where we were churning the image, the record was an image, right? That was a record. An image was a record. And in this case, what we are doing right now, you see the temperature processing. Each line is a record because against every record, the mapper will be executed. So you will have to define, you'll have to give a definition of a record. And how do you give the definition of the record? By telling MapReduce job that you're processing this kind of data and use this kind of input format. By default, if you do not tell MapReduce that the input format, it assumes it to be text file. And when it assumes to be the input to be text file, every line, meaning record separated by new line. So every line is a record. Okay, every line is a record. So we'll talk about input format a little bit later. So input format converts raw data into something which MapReduce understand. Okay, so that Hadoop can execute your mapper against every record. So input format contains raw data into records. All right. I hope I was able to answer your questions. So question from Seek is, so sort is followed by grouping in the mapper. So it is outside the mapper logic. Just as we finish the mapper logic, Hadoop will, as soon as Hadoop finishes running your mapper against every record, whatever is the output of all the mappers, it will be sorted and then grouped on the same node. Uh, on the sorry, it'll be sorted and grouped on the same node and then transmitted to the reducer node. All right. Yes. So you've understood it correct. Churning data, churning image means processing data or processing images. Okay. Here in the earlier example, this is what we call churning data, as in converting images into some other form, transforming or translating or processing and churning data. Okay. So yeah, I use that word quite often. All right, to an extent, I think I've used churning in my LinkedIn profile as well. All right, okay. So moving ahead, I hope everybody's with me so far. Uh, okay, at least I can see all the participants are there. Nobody has exited yet. All right, that's wonderful that everyone is awake. All right, so this is how, if I have to write a MapReduce logic using for computing max temperature of every city, this is what I'm going to do. But you don't need to use MapReduce for such tasks because most of these tasks can be very well performed by using SQL query via Hive, and Hive will translate internally the SQL query into something like this. Now, the previous example where I tried to show you what happens when you have single node. But in case you have multiple nodes, both the nodes are running the same map logic parallelly, which means your piece of code that you call that this is my mapper, that mapper get transferred to every node. So the code travels to every data node and cloned everywhere and then executed against the records. And then after every node has finished sorting data, it gets merged. Okay, so you can see that here, stage number 1, you have Sa, Re, Saga. Here on the second one, you have, let's say, Sa, Re, Sa. I'm just taking very simple examples of records because uh, I can't really fill the screen. So imagine that there are two lines of text, first line on node 1, second line on node 2. First line converted that data into key and value like this, Sa1, Re1, Sa1, Ga1, and second one converted that into this form. And then the third, here at the third stage, on both sides, you see it gets ordered and then must. Ideally, here itself, the grouping and merging happens. So yeah. Actually, no. The grouping doesn't happen on individual node. It's only sorting that's happening. Grouping happens while we are executing reduce. Before executing reduce, grouping happens. All right. So before executing reduce, the grouping happens. In another beautiful way, this is how it looks like. You have multiple map phases, and then the data get copied over the network. This is the network onto another node. This is also another container, by the way. This is a container, this is a container, this is a container, this is a container. It's not the application master. Okay, so application master is just launching these processes on various containers and then telling them what to do when. Okay, so I hope this is clear so far. Now, sometimes, as Kush has already pointed out and others have also pointed out, one reducer may not be sufficient because you are all the workload of merging is on one machine. In case your merging is too intensive, okay, in case your merging of data is too intensive, you may want to specify that we want multiple reducers. You may want to specify that you want 2 reducer, 3 reducer, or 5 reducer nodes. Okay, and if you have like 2 reducers, there will be 2 buckets created on every machine. Some of the keys will go into one machine, one bucket. Some of the another keys will go into another bucket, and these buckets will be carried to the reducer node. Okay, all right. So some of the so all right. Let me take a step back. If you have n number of reducers, there'll be n buckets created for every reducer on every node. And these buckets will be carried onto their corresponding reducer node. Okay? So if we specified 10 reducers, how many buckets will be there here? Correct. There'll be 10 buckets and will be carried here. Now, total network transfer is how many? How many network transfers are happening here? In this case, we have 3 mapper, 2 reducer. How many network transfers are happening? 6. Correct. From every node, the data is getting transferred to every other reducer node. Okay, so in case we say that we have 5 reducer node, how many total network transfers would happen? If 3 mapper node and 5 reducer node, 5 into 3, correct. Okay, so that means if we keep on increasing the number of reducers, the total network overhead will keep on going up. Okay, it'll keep on going up. So MapReduce is very analogous to group by clause. The way, if I have to do the same max temperature problem, I'll say select city comma max temperature from table group by city, right? We did not write any logic where we are where we are sorting data. We are letting SQL sort the data, right? We are letting SQL Server sort the data. We are not ourselves sorting the data in case of SQL. We are not writing for loop or any other strategy. Okay, all right. And similarly, if you see this SQL query is nothing but kind of map reduce. So in map, you do select, right? Select, you say, you specify that group the data by city, group the data by city. In mapper, you specify that, okay, this is my key, so group the data by this particular column, and so on. All right, and the reducer part, you see, in that we are computing max. All right, so yes, looks like I quickly went ahead from multiple reducers. Okay, let me try to take a step back and try to explain. Okay, a question from Mohit is that wouldn't we need these two parts? So if you see in this diagram, okay, let me explain again. Yeah, so we have input data block. Okay, uh, I think this is something I would love to explain. Or okay, I will anyway cover something called input splits tomorrow. I will talk about input split. So the raw data from, okay, let me try to draw. Okay, raw data from, let's say this is, okay, I cannot annotate here. All right, so raw data from HDFS will come here. Okay, so Raw data will be on every node, data block 1, data block 2, data block 3. And from that data block, this input split is being created, right? If I could. All right, let me try to draw on it. Okay, so let's say there was a data block here. Okay, this is block 1. And from that, this input split will be created by the way of something called input format. Input format. Okay, so every block will get converted into some meaningful bunch of records. This is a group of records called input split. Now, against every input split record, okay, so input split is, you can always think of input split like records. Okay, every record could be a file, could be a JSON, could be a big object. So this is what it contains. Okay, so input split is basically a group of records, kind of array of records. Okay, against every record, my map method would get executed. Okay, against every record. Now the output of map would be key and a value, right? Output of map would be a key and a value. Key could be anything that you wish to print out, because based on this input object. Okay, from input object, your mapper function will print out something, right? Let's say you talk about word count. So in case of word count, it will be a line. It could be a, let's say, line of text. So your map function will break down this line into key and values, and then it will basically generate key comma value. And this bunch of key values get sorted and stored in these buckets. Okay, stored in these buckets, and these buckets are carried to different machines, and there the merging happens. The merging happens on every node. Okay, now question is, which which key would go to first machine, which uh, key will go to second machine? The answer lies in something called partitioner that we'll discuss later. So internally, the hash code of every node is, every key is computed, and based on the hash code, if it's, let's say, the hash code is divided by total number of nodes, okay, and in case the remainder is 0, it goes here, or remainder is 1, it goes here. All right, so what I'm trying to say is, all right, this is a little tricky, so be with me. Okay, so I'm trying to say is, let me first define something called hashing. Okay, what is hashing? Converting a name to a number. All right, so this is called hash code generation. All right, let's say Sandeep results in 54. Okay, so 54 is basically further divided by total number of nodes, a reducer node, let's say 2. What is the remainder? 0, right? That means Sandeep key would go to the first reducer. Okay, did it make sense to you? Which also means Sandeep key would go to first reducer on every node. Okay, let's say another key was let's say Nitin. Okay, and this one is 71. This hash code generation could be as simple as summing all the numeric value of every ASCII code and dividing by 255 and keeping the remainder and so on. Just converting every string into something numeric. Okay, so 71 divided by 2, the remainder is how much? Percentage, percentage. And the remainder is 1, therefore it goes to the first one. All right, had there been 3 nodes, so it'll be divided by 3, and whatever is the remainder would basically signify which reducer it would go to. Make sense to everyone? So this strategy is default strategy in Hadoop. Okay, this strategy is default strategy in Hadoop. You can override this strategy by defining your partitioner. Okay, all right. So as part of MapReduce job, what are the things do we pass? Who can help me? File / folder. Okay, good. Then and format. Okay, good. This is optional. All right. By default, it considers the input data to be text file. Mapper logic. That's good. This is kind of mandatory. Okay. This input format is the input splitter. Yeah, this we have considered. Omkar and Thomas and Sapna. Okay. Yes. Partitioner logic also. Yes. Sometimes this is optional. By default, it does it the way I have defined, convert the name into a number and then uh, divide it by total number of reducers, as in it does the round robin. Okay, it's like had there been 3 reducers, so had there been like 3 reducers, so and so it would basically try to send those same to. All right, now questions from Priya is both buckets contain same data. Okay, so no, they'll be splitted, but everywhere if Sandeep from this map function has gone to first node, Sandeep will also go onto the same node here. Let's say we were using the word count example. If the encountered on this map went to the first reducer, okay, and so on, then the would also go here on the first one. So, all right. A question from Saptarishi. What determines number of reducers? We will talk about it. We specify number of reducers. Okay. Why will network utilization go up? By example 5 by 3 for 3 reducer if I send the same number of keys to the reducer as to the only one before. Okay, let me reread it to understand. Why will the network utilization go up by 5 into 3 for 3 reducers? Okay, if we have 5 mapper and there are 3 reducers, then the total network communications would be 5 into 3. So if I send the same number of keys to the reducers, okay, as to the only one reducer before. Good point. So question from him, from Thomas is very interesting question. Question is, earlier in this case, same data was being passed to a single node, while same data is being passed to two nodes. So on an average, the network, so the data is same whether we send it to two nodes or one node. Okay, but if you take a look at the total number of connections that will get opened would be more in this second one. Therefore, the network total number of connections will be more, although the data transfer will be less. So uh, uh, the overhead that happens in case of network connectivity, that will be higher in this case. The overhead will be lesser in this case. All right, because there's a lot of overhead that exists because of number of connections. Okay, for example, 90% of our time in case of opening a website goes in establishing a connection. Okay, DNS lookup and etc. That's the reason. Very great set of questions. All right. Now, next thing, what else? Number of reducers. Okay, number of reducers. And this, if you only have more than one reducer, only then this partitioner logic comes into play. Okay. The output, we forgot something in the beginning. It's called output location. Okay, this is input file folder location. Okay, now a very good question from Ted. This is something I think multiple people have asked this. Is the output of multiple reducers be further aggregated? Good point. And this is a very interesting question. So when we deal with big data, and sometimes when we are using MapReduce, the result of reducer phase might be splitted. Okay, so the general trend is that we do not try to concatenate these files. Instead, we override the partitioner such that we control what goes in part 0 and what goes in part 1. All right, let's say your input data contained males and females data. Okay, you wanted to keep males in part 0 and females in part 1. Then you will override the partitioner in such a way that all the males will go in the first bucket, and all the females go in the second bucket, and so on. So generally we do not need to concatenate this. All right, but if needed, you can you might have to sometimes do the further processing in order to concatenate these. Let's talk about word count example. Uh, okay, I did not get your question, Nada. So HDFS replication, you mean this part? Okay. So this output of the reducer is going to go into HDFS, and then the usual process of HDFS of creating replicas will start. Okay, this file will also get replicated. That's all it means. All right. So, okay. So this was, I think, I hope I have kind of answered your questions. And also keep in mind that this merging is not too intensive because this data that is coming from all the nodes is already sorted. Therefore, merging on every node is already sorted. Let me try to give you, take you through one example of, let's say, or we will actually talk about partitioning again in details. Okay. So, all right. So this is what is MapReduce. All right. We will continue from MapReduce quick questions tomorrow. And we will also do a couple of hands-on exercises tomorrow. All right. So today we have covered a great deal of MapReduce. Tomorrow we will basically go through examples and do the hands-on exercises on MapReduce. Okay, great. All right. Thank you, Ali. Thank you, Anup, Arslan, Barsa, Jamil, Jinyang, Jitendra, Karthik, Kush, Manjunath, Mohit, Nada, Nitin, Omkar, Prashant, Priya, Ramana, Sapna, Saptrishi, Sheikh, Stephanie, Sundar, Ted, and Thomas. All right. I look forward to see you tomorrow in the class. Okay? Yes. Bye-bye. Have a great day. I see. All right.